The purpose of today's lab is to find the spring constant of a particular spring. Now, you've got to write down a problem, and that problem is always going to be phrased in the form of a question, but you can probably, without too much effort, rephrase what I just said in the form of a question. You want to find the spring constant of a particular spring. You're going to have three sets of variables: manipulated variable times 1, responding variable times 1, and control variable times, well, really, there's an infinite number of control variables. I don't expect you to list an infinite number of control variables. I expect you to list a few, and especially one or two that are particularly important. In this lab, as in any other lab, if you miss the one or two really, really, really important ones, that's when you tend to lose marks for your variables. Now, your materials, I'm not going to tell you what those variables are, by the way. As we go through the materials and the procedure, I think it should become fairly clear to you what those variables are. Materials are quite simple. You're going to use what's called a Hooke's Law apparatus. That's what this is, a Hooke's Law apparatus. It's a kit that we buy that allows us to attach a spring to it and masses to it, and then do an analysis to find the spring constant of a particular spring. Hooke's Law apparatus. In addition to the Hooke's Law apparatus, though, you are going to need to use a spring. Now, the spring for you may be in the kit, but it's not a part of the kit. So you need to list it separately. You've got your Hooke's Law apparatus and you've got a spring. In addition to that, the third and final material will be a mass set. You need to use a mass set to put on the spring to ultimately find the spring constant of that spring. Now, how are you going to do this? Well, the first thing that I'd like you to do is to attach the spring on the hook of this Hooke's Law apparatus. You're going to notice here when I blow this up a little bit, make it a little bit bigger, there's a ruler on the back of this Hooke's Law apparatus. It's adjustable. You can move it. There's little handles on the back of that ruler that you can squeeze together and move it up or down. You want to make sure that you move it up or down so that the bottom of the spring is in line with 0. In other words, you need to zero this scale. You need to tear this scale so that the initial displacement is 0. Then you're going to put a mass on the end of this spring. Now the mass is going to come in a mass set in these green boxes up here. These mass sets are really, really handy for this activity because they are what we call slotted masses. There's a hook, and then this little rod that goes down from the hook to the bottom mass, which is attached to the whole thing. But the rest of the masses can come on and off simply by going up and sliding it off, or sliding it on and then allowing it to go down. You want to apply a mass to this, and you want to see how far it stretches as a result of applying that masses. Apply a mass, see how far it stretches as a result of applying that mass. What are we really doing, by the way, when we apply a mass? Not so much applying a mass, or applying a force, right? So apply a force with the mass, and then see how far it stretches as a result of that. And then change the mass. And it's easy to change the mass on these sets because, again, all you have to do is slot one of these masses on and then let it drop down and record its value. Now, just one little thing about the mass set so that you understand how it works exactly. If you take all of these masses off except the bottom one, which is attached, you're going to see the bottom one has 50 grams printed on it. It says 50 grams. That is the mass of the mass at the bottom, but it also includes the rod and the hook, because that's all part of the bottom mass. Does that make sense? So you don't have to add the mass of the hook and the mass of the rod on there. That's included with the 50 grams on the bottom. The other ones also have the mass printed on them. All you're going to do is simply add it to the 50 grams that you used on the bottom. Cameron? Yep. Good question. Hey, that's the question that I was going to answer later on. But yes, the force that you're applying is mass times gravity. Yeah. You're going to, of course, repeat that, right, with different masses and get a bunch of different forces and a bunch of different displacements that correspond to that. Now, this is a picture of when we're collecting data. You can see the mass set is right here. You got one mass that's attached to the rod here, and then you got one mass that's on top of that. So our mass isn't 50 grams. It's whatever this 50 grams is plus whatever this is. Now, what would be my displacement if I was to look at this as my data? What would be my displacement? Where do I measure my displacement from, Simon? Exactly, exactly. And that's the reason that I showed you this picture and this picture is because I want to make that point that we have to be consistent where we measure it from. Here's what some people do say, oh, you know what, it's a little bit easier to measure it down here from the top of the masses. Well, that doesn't work unless you measure it from the top of the mass every time. And the top of the mass is the same place every time. You got to measure it from the same place. Since we measure it from the bottom of the spring here, we're going to measure it from the bottom of the spring right here. So my displacement in this case would be 3 centimeters. Your data table will look like this, or at least something like this. I've got mass in grams and displacement in meters. You may automatically convert the grams to kilograms and just record it in kilograms. That's fine. You may record the displacement in centimeters and then convert it to meters later on. That's fine. I don't care. If this was a test, you could record the data in whatever units you want. Meters, centimeters, grams, kilograms, whatever, as long as you specify the correct units. You're going to have 10 trials with 10 different masses. And then, of course, you're going to have 10 trials with 10 corresponding displacements. What do you think you're going to do with this graph? I'm sorry, what do you think you're going to do with this table? Sorry. We are going to ultimately turn it into a graph, but we have to do a force displacement table first. We've got mass displacement. This is data. Remember, anything you collect in the lab is data. As soon as you do something with it, as soon as you do a calculation, as soon as you analyze it in any way, that's analysis. You need to include your data table. You also need to include your analysis table, which is force and displacement. Displacement will be in meters. If you didn't put it in meters in your data, put it in meters now. Force is going to be in newtons. If you put your mass in kilograms, then multiply kilograms by 9.81. If you put your mass in grams, then divide by 1,000 and then multiply it by 9.81. This force, the applied force, is the force of gravity, mass in kilograms times 9.81. And of course, now we're going to plot a graph. What's going to be on the x-axis of that graph? Displacement or force? The x-axis of your graph, is always going to be the first column of your table. So the x-axis of your graph will be force. And of course, your y-axis will be displacement. Don't forget to title this. And just a word of caution. A lot of you make this mistake when you're writing up a lab and plotting a graph. You highlight all your data, including your headings, and then you insert your chart. If you insert your chart after highlighting everything, including your headings for your columns, it will automatically give you a title that is backwards. And some of you have lost marks on that over the last several labs because you insist on having Google Sheets title it for you. But Google Sheets doesn't do it right. It plots everything right except the title. The title should be y-axis versus x-axis. So my suggestion for you would be highlight your data, but don't highlight the headings. Then you're going to have to insert your own title. And when you insert your own title, you're going to stop and think about which way it should go. It should always go y-axis versus x-axis. In other words, in this case, it would be displacement versus force. When we plot this graph, we will get a straight line. All of you will get a straight line, almost a perfect straight line. But we have to figure out how to find the spring constant from this straight line graph. So we're going to do an analysis that we've done once or twice before with some of the labs that we've done. We're going to come up with an equation from the graph, and then we're going to come up with an equation from our data sheet. And we're going to compare the two and ultimately figure out what the slope of this graph represents and how close it is to the spring constant. What's the equation for this graph? What's the equation for any graph that's a straight line? Y equals mx plus b. You will find that the y-intercept of this graph is either 0 or very, very close to 0, close enough that we can scratch that off. What's the y-axis of this graph? What's on the y-axis of this graph? Displacement. Be careful with this, okay? The displacement of this graph is the y-axis, and the symbol for displacement is what? No, that's the units. No, not delta D. Delta D is displacement. How far has the pen moved when I throw it across the room? It's x. So be careful here, okay? We're putting x in there not because we're representing the x-axis. We're putting x in there because we're representing the displacement, which just coincidentally has a symbol of x. Does that make sense? This x and this x are not connected in any way. Now, m represents what? Slope. X represents the force. Good. Now we have to come up with an equation from our data sheet that has both f and x in it, the same two variables in it. What is that equation for my data sheet that has f and x in it? Good. F is equal to kx. Is it kx or negative kx? It should really be kx here because we're talking about an applied force here, right? Gravity is the applied force, not the restoring force. So it should be kx versus negative kx. I wouldn't lose any sleep over that, but it should be positive. Now we're going to rearrange this to take the same form. So if this one has x equals something, then this one has to have x equals something as well. If we rearrange f is equal to kx to solve for x, it's going to be f over x. And now we want to scratch out things or cross off things that appear in both terms. X appears in both, so let's get rid of it. F appears in both, so let's get rid of it. What are we left with on the left-hand side? Slope. What are we left with on the right-hand side? No, not k. 1 over k. Right? K's on the bottom, so it would be 1 over k that we're left with. Therefore, the spring constant k is equal to 1 over the slope if I rearrange that. So what you're going to do is get the slope of this graph the normal way, the way that we have for every graph that we've done this year, and then you're going to flip it over, take the reciprocal of it, and that's going to give you the slope of the graph. It should be a relatively small value because we're dealing with springs that aren't particularly stiff. If you forget to convert units, you will get a value that's way off, conceivably off by a factor of 1,000. If you're supposed to get a spring constant of 25 and you get a spring constant of 25,000, that's a pretty quick indication to me when I mark it that you forgot to convert units, right? It's an easy check for me because if your spring constant is off by a factor of 100 or by a factor of 1,000, then that means you forgot to convert centimeters to meters or grams to kilograms. If it's off by a factor of 10, well, that's a tougher one. If it's off by a factor of 10, that's worse.
It means you change it just wrong.
No, it means you forgot to convert centimeters to meters and you forgot to convert grams to kilograms. It means you forgot to do 2 conversions. Bottom line is, I know what to expect. Your spring constants will all be a little bit different, so don't worry if yours is different than yours, but they're all going to be in the same order of magnitude. So be careful with those conversions and make sure you get that spring constant that is what it's supposed to be. All right, what comes next? Conclusion. Conclusion is just simply, what did you learn? Okay, what is the value of the spring constant? And how do you know? This is not a place for calculations. Somebody in the last class was asking me about that. Conclusion is not a place for calculations. Data is what you record in the lab. Analysis is when you do something with it. Your conclusion is just a summary, right? All you're doing is summarizing what you've learned in your conclusion. Don't show me the analysis in your conclusion. Show that in your analysis. That's what it's called, analysis. And then, of course, your sources of error. You want to have a few good sources of error, including suggestions for improvement. What you don't want to say is, I made a mistake calculating force. I forgot to convert meters to centimeters to meters. Fix it then. Okay? Calculation errors, human errors like that are not good sources of error. If there's something else that could lead to inaccurate results, then, or something else that could lead to you doing this lab quicker or more efficiently, then include it. But let's not include things like human error, like I made a mistake calculating, or my partner wasn't very smart. I've had it before, yeah. What do you got to do for this? Summary, what do you got to do for this? Basically, it's everything except hypothesis. It's your problem, phrased in the form of a question. It's your variables. It's your materials. It's your procedure. Remember to number that procedure, right? 1, 2, 3, and so on. It's your data, which includes just a simple table that you collect in the lab. It's your analysis, which actually includes quite a bit for this. It includes your table, your analysis table, that is, not your data table. It includes your graph, and then it includes the analysis after the graph to figure out what the spring constant is. And then, of course, you have your conclusion, and you have your sources of error.